In this video, we are going to be reviewing the topics from week 7 of Statics 202, which talks about trusses and method of joints and method of sections to solve forces that are developed internally within trusses. Okay, so trusses are a series of beam members joined by pins. So, each link, there's a pin that holds it together, and these pins are the key to help us find internal forces developed within trusses. So trusses can look like this. They can look like this. Right, so basically the frames that you're used to seeing in bridges, for example, right? So there's lots of different members that are being used in these kind of problems. So there's going to be a lot to break down for your forces. So I'm going to talk about two force members and directions of forces. So if we had a frame that looked like this, and we're going to separate it into 3 different sections. So if we started with this blue section down here, so like we said, these are all joined with pins. So this would develop a reaction that is, sorry, I apologize. Sorry, we're going to start with the pins. So if we had 3 different pins in this structure here, right, we had another pin here and one more here. If we were to draw out these pins just without the connecting beams between them, you want to draw them, the forces, the internal forces, as a result of them being under tension. So for blue, this could be, so let's call this A, B, C. We could call this FA, and we could call this FAC. Sorry, AB should be here. And for red, it's going to be pointing in the opposite direction, right, to the one that we established on this beam. So this is all one beam total, but we draw each one as if they were under tension. So this would be FAB as well, and this is FBC. Okay, and we have another FBC pointing this direction from this joint, and pointing FAC. All right, so basically this is an introduction to the method of joints, where we're going to separate our forces by looking at each individual pin and just assuming the direction. Similar to moments and our other equilibrium questions, if the assumed direction is negative, then that just means it's truly in the opposite direction. So that's what we're going to be using to kind of introduce you to this method. Yep, so that's what we just covered for this one. So now let's take a look at one that might have multiple different reactions going on with it. So this would create a Y and an AX reaction for this pin right here. It also creates along our beams. These are the internal forces. This is FAC and FAB. We also got FAB pointing here, FBC, and we have an external force of 500 newtons. And C is a rocker, so then we have a normal force, I'm going to call NC. This is FBC and FCAC. So by splitting all of these pins up, we can simplify it and solve for any unknowns. So here in total we have 1, 2, 3, 4, 5, 6 unknowns. And we're going to talk a bit more about how we would solve these unknowns. So if you were to solve for these equations, you would have to solve for each one on its own. So if I did this top joint B here, I would have to make two equations for this one on its own. So for fx and fy, so there's two unknowns and two equations. So let's start with this one first because the other unknowns rely on these two values. All right, so if we were to do this, this would be in our x direction, we've got 500, positive x direction, and we've got negative FAB. And we have, so this is an angle of 45 degrees as well. So this would be FBC, and it'd be pointing downwards, so FBC, and that'd be sine, no, that'd be cos 45 equals 0. So each one's going to have its own x and y equilibrium equation. And this will be plus FBC sine 45 equals 0. Right, so you would find FBC is equal to, so that's negative 500 divided by sine 45. And this is negative 707.106. So negative 500 divided by sine 45. And then you'd find FAB equal to, so this is, so negative our answer times cos 45, which is equal to 500 newtons. And you would use these to solve for the other unknowns. So you could do this for our pin C. So same thing, each one gets its own equilibrium equation. This is equal to, okay. So our upwards force, this is positive our normal, and this is minus FAC minus FBC. This is 45. And this would be cos 45. And so we only really need our y equilibrium equation. And this will be plus FBC sine 45 equals 0. So then we can find our normal force to be equal to, so BC was negative 707.106. And that's times sine 45. And move it to the other side, that is positive 500. And we can use our, at pin A now, we develop our two equations. It's equal to, so we have AX plus FAC, and then we have AY plus FAB. So then AX is equal to, oh yeah, we still need to find FAC over here. Sorry. So then FAC is equal to, so that's 500 and then that's cos 45. So that's 353.5, and that's negative. So this is equal to positive 353.5 newtons. And our AY is equal to our FAB, which is negative 500 newtons. So let's use, you can use 6 equations to find 6 unknowns, ensuring that each pin has 2 equations each. Right, so you want to start with the pin that has the least amount of unknowns, because that'll be the simplest to solve, and you can use those unknowns to find the reactions in our other pins. Okay, so next we're going to talk about zero force members. So when 2 non-collinear members are joined by 1 pin, and no external load is on the pin, one beam is cancelled. And bears no weight, bears no force. So remember, non-collinear means that they are not in the same line. So if you had something like this, and this is your pin here, they would be non-collinear, joined at this pin. And if there's no external force acting on this pin, then this beam would get cancelled out and would be a zero force member because it wouldn't bear any weight. So we want to look at these examples here and see what we can eliminate. So it's kind of similar to our process for 2 force members. It's going to simplify the amount of unknowns that we need to solve and reduce our complexity for a question. So let's draw the reactions that we would have. Okay, so we know that pin F, pin B, and pin C all bear external loads or external reactions. So let's start at pin A and see what is going on. So we have 2 non-collinear beams that are attached at A, right? And we see that pin A itself isn't actually holding any load, right? There's nothing acting on that pin. Because they're not collinear, then that means we can cancel out both of these beams. Okay, so beam AF and AB are both zero force members. Okay, let's check out D. So pin D has 2 beams that are not in the same line, so they're non-collinear. And D does not have any external force on it, so that means that we cancel those 2. And the reason that E and B stays is because we have this force acting on B. So because this is in the same line as where the force is acting, then this member will bear load, will bear force. So we have to keep everything in here. So if we were to redraw this, this beam simplifies down to this after we cancel our zero force members. Okay, with our roller here, our downward force. Okay, so that is our first one done. Now let's check out this one. So we know E is already occupied with a force. We have an external reaction, normal force from our rocker. And from this point we have A, Y, and AX reactions. So let's take a look at pin D. Pin D has this beam attached to it and a non-collinear beam attached to that same pin. But since this outer one bears load, then we have to keep this one for sure. But since there's no external forces on D, on this pin, then that means we can get rid of this member here, right? Because this one bears no load. Same with C, there's nothing acting on this one. So this beam right here can also go away. So that just leaves us with a beam that looks like this. So this skill is going to become useful when we're looking at trusses that have a lot of different members on them, and it's going to simplify the amount of unknowns that we need to solve for. Okay, so we're going to start with this question here. The very first step is identify zero force members. So this is a good rule of thumb for your first step because it'll make the rest of the equation a lot easier. Okay, so we know that we have two reaction forces from our supports. All right, and then I don't believe we can cancel out any of these because if we were to remove this beam, for example, the body would deform, right? We would see that this part would collapse. So all of these members are integral in maintaining the shape of the rigid body, so we don't have any zero force members in this question. Okay, so let's start with pin A. Okay, so this is pin A. And if we were to draw the free body diagram, this is, let's call this FAD, and this is FAB. Okay, and this is at, so if we just take this triangle here, so we can find our angle that it makes, this triangle here has a height of 1.5 and a length of 2. So if we do tan inverse tan of our opposite over our adjacent, this gives us, so it's 1.5 divided by 2, and this is 36. Okay, and we also have this external load of P, and this is equal to 5 kilonewtons. So we can solve for these two because we have two equilibrium equations. So this is going to be sum of x is equal to 0. So this is going to be the x components of both of these, which is in the positive x direction. So that's FAB, and then that's cos 36.869 plus FAD cos 36. Okay, and our y, we have one of these pointing up and one of them pointing down. So these are actually going to just cancel in this case, I believe. So this is going to be negative 5 kilonewtons down. And then we have positive FAD sine 36. And then we have minus our FAB sine 36, right? Because our component for FAB points down and our component points up for FAD. Okay, so we're going to have to solve for in terms of one of our equations. So let's move our 5 over, and this is FAD minus FAB, and this we can factor out our sine 36. Okay, so let's move that over. So this is going to be 5 plus FAB over sine 36.869 is equal to FAD. Okay, and if we plug into our fx equation, then this will be so if FAB cos 6 and then FAD is, hold on. So if we plug into our equation, then we see that FAB becomes negative 4.167, and FAD equals positive 4.167. Okay, so what this means for our FAB is that the direction that we assumed was incorrect. So instead, this will point in this direction, meaning that that beam will be under compression. Okay, so I don't really have enough room to finish the rest of this question off, but if you use the same kind of logic that we did for this previous example, where you're going to take each separate pin and make two equations for it to find the unknowns, then you'll be able to finish the rest of this question. So I'll leave this on screen for you guys to try. So you're going to need to find the internal forces from D and B. You're going to need to find it from B to C, D to C, and D to E, as well as all of these support reactions. Okay, so I'll leave you guys to do that. In the meantime, I'm going to move on. So I'm going to talk about method of sections. So method of sections is taking, rather than breaking out each pin and solving for the internal loads from there, if we want specific internal forces, we can use method of section. So what we're going to do is we're going to split down where all sections are present. So we have EF and FC and BC. So we want to cut down here because it would cut through all of those three members. So once we cut that in half, we're going to develop two different halves. So this is for G. And then at the cut, you're kind of going to just have these little straggler forces here. So it's going to be F, BC, F, FC, and F, FE. And at the other side of the cut, kind of like our joints, is just going to be facing the opposite way. Or it will look like this. So this is F, FC, FBC, and FFE. And that looks something like this. We're going to add our external loads and 4 here. So we want to determine if these three forces are under tension or compression. So in our method of sections, we have 3 equations that we can use for either side. So for either side, you can use your sum of x fx equal to 0 equation, your sum of xy equal to 0, or your sum of a moment equal to 0 at any point. And this will be most useful to help you find external forces. Right, so where we have our support reactions here, that will be useful to determine. So I'm going to start with our right side for this method. So with our right side in yellow, so since our left side has a lot of different things going on, we have 1, 2, 3, 4, 5, 6, 7 unknowns. Be good to start with the right side because we have 1, 2, 3 unknowns. We have 1, 2, 3 equations that we could use to solve it. So if we start with our Fy direction, that means we would have, so this is 45, because the height and the width are the same. So this would be F, FC, and this is 45. Sorry, sine 45. And then we have our external loads, so that's -3 minus 4. And we could solve for our FC right here, so we can solve for our first one. So this is equal to, so that's 7 divided by sine 45, and this is equal to 9.89, and this is positive, so it's under tension. So the initial direction that we assumed, where it's under tension, is correct. Okay, and let's do our x is equal to 0, so this is cos 45. This is minus FBC and minus FFE. So this will give us FBC is equal to, so let's take this value and this cos 45 times our answer, and this is going to be negative 7, right, is equal to FBC. And let's use our moment as well. So where should we put our moment in this case? So like our previous questions, we want to choose where it would be best to put our moment. So we want to choose a point that has the most reactions or forces coming out of it. So that would be point C here. So we're going to do it at point C. So that means everything going through it we don't use. So we have FE and 4 left. So we have FE, and this is at a vertical distance of 1. And this would be going counterclockwise, so that's positive. And this is going clockwise for our forces, negative 4 at a distance of 1 from point C. And that means that FE is equal to 4. kilonewtons. It's positive, so it's under tension. And then we can use that to find FBC. So going back to our second equation, FBC is equal to, so that's negative 7 minus 4, and that is negative 11 kilonewtons. Or you could say, so because the negative sign, it means it's in the other direction. So this would be in compression. Okay, and that's all we need for this question because it's not asking us for the reaction forces. So that's it. But you could use these forces then to determine the external loads, the external reactions. But this is how to solve this equation using a method of sections. So we're going to do another example. So determine the forces of members ED, BD, and BC. So this ED, BD, and BC. So that means we want to cut it here. So when we cut that, let me draw the left side. So the left side is going to look like this. It's 800 newtons. It's 500 newtons. Okay, and then this is where we're going to have our cut. So that looks like that. So this is our forces. And then for our right side, we have something like this. And we have support reactions from these two. So there's a roller at C. And then we have dy, dx, and cx. And we have our unknown forces. So this is FED, FBD, and FBC. So we're going to solve for those. So we're going to choose an equation, a side that has the least amount of unknowns. And for that, I would choose the left side because we have 1, 2, 3 unknowns, whereas our right side, we have 1, 2, 3, 4, 5, 6 unknowns. So do our left side. Right, we have our downward forces. So this is our y direction forces. So this is negative 800 downwards, minus 500. So these are the external loads. And this is going to be plus FBD. And this is 45 degrees. This is FBD cos 45. Okay, and we can solve for FBD right here. So this is going to be equal to, so let's move that 800 and that 500 to the other side. And then this is divided by cos 45. And this is going to be 1,838.478. And this is newtons. And this is positive, so that means the direction that we assumed was correct. So this is intention. Okay, let's do for x. This is equal to, so we have, actually, let's start with our moment first. It'll be easier to solve. So let's do our moment at wherever there is the most forces coming out of. So that would be point B. So I would do it about B. And once we do that, we eliminate FBD and FBC because they are coming out of that point, so then they would not contribute to the moment developed. So this would be 800, so that's our external force, and how far is it? It is 6 meters to B, right? And we would have to go in a counterclockwise direction, so that is positive. And then for our 500, this would have to shift also 3 meters. So this would be 500 times 3. And we would have to go in a clockwise direction to get there. So this is in a counterclockwise, so that's positive. And finally, we have our FED up at the top. So FED would need to go in a counterclockwise direction to get to B. So we have FED, and that is at a distance of, so it's a vertical distance now. And we want that vertical distance of 3 meters equal to 0. So we move this over. So we have FED is equal to, so that's 800 times 6 plus 500 times 3. Okay, so that's 800 times 6 plus 500 times 3 divided by 3, and that's 2,100 newtons, and that's positive, so that means this is intention, so the direction we assumed was also correct. Okay, and our last part is with our x components. So this is FBC plus FED and plus our FBD sine, cos 45. Well, it would be the same anyways. Okay, and this will give us, so our last one is FBC, I believe. And this is going to be negative. So this is negative 2,100. And this is minus 1838.478. And this is going to be negative 3,938.478 newtons. And this can be rewritten as newtons in compression because of our negative value. Okay, so again, always choose the easiest side to solve. Okay, so that is it for this example. And that brings us to the end of the video. So in the next video, we're going to be doing some sample questions that relate to both of these methods. So if you're asking yourself which method would be the best to use, so if you're asked for the forces in every pin, then it'd be good to use a method of joints in that case, where you break up each joint and you look at each pin and make 2 reactions for each pin. But if you're just asked to find the forces internally in specific members, and you can see that you can, in fact, section them out using method of sections, then I would recommend using that method because it would save you a lot of time. Of course, you can use either method, but whichever one suits your needs best, definitely use them. Because if you used method of joints for this question, for example, it would have taken longer to do. You would have gotten the same answers, but this one is just a lot easier to do. So when you use method of sections, make sure that your section cuts through all three of the members, and that you choose a side that is easiest to solve, that has the least amount of unknowns. Okay, so I will see you in the next video when we will do some more practice for either of these methods for our trusses. See you there.